So I'm going to be skipping around as we did this yesterday. Half of it with other classes. So let's start with number one. So we have lithium and chlorine. How many valence electrons does lithium have? It has one valence electron. How many does chlorine have? Seven valence. Does everyone understand how we're getting these numbers? Yes, sir. So the first column is 1A. The second column is 2A. We skip over the transition metals. 3A, 4A, 5A, 6A, 7A, 8A. So chlorine is in 7A, so it has 7. Lithium is in 1A, so it has 1. So Lewis dot structures. So basically, like, how many valence electrons does carbon have?
Carbon, 4.
4. When you write the Lewis dot, try to spread out all the dots. Basically, these dots represent how many valence electrons it has. Don't put them all on one side. And the most they can be on one side is 2. Don't put the 4 like this. Because we can spread them out equally on the 4 sides. So don't do that and don't do this. Spread them out. So lithium has 1 valence. And chlorine has 7. Besides hydrogen and helium, every element wants to either have 8 valence electrons or 0 on the outer one. Basically, it wants to either get rid of its outer shell or fill it up to 8. So it either wants to lose or gain. So we notice that chlorine has an empty spot from being having full 8. Lithium has 1 additional valence electron, and it would happily like to get rid of it. So it's going to transfer it over to chlorine. For Lewis dot structures, if it's an atom, we do this. And when it removes this electron, it becomes an ion. What is an ion? It's an element or molecule that has a charge. So when it loses this electron, it no longer has any valence electrons on it. So, theoretically, it now has a new valence electron, but the original valence shell has 0 on it. What would its charge be when it loses 1 electron? So it would be lithium plus 1. We usually don't include the ones, but I'll do it for charges. So it becomes lithium plus 1. Now chlorine has gained this dot right here.
Have a negative charge.
Yes, it have a charge of -1. And it has now 8 valence electrons on it. So lithium will transfer 1 electron to chlorine. Chlorine will accept 1 electron from lithium. Let's do number 2. So we have calcium and oxygen. How many valence electrons does calcium have?
Can we just put one electron to see it? Instead of allow electrons. For the boxes. You put allow electron.
Yeah, you could put one electron to chlorine. So how many does calcium have valence electrons? 2 valence electrons. How many does oxygen have? 6. So we're going to come over here, draw the Lewis dot structure for it, and come over here and draw the Lewis dot structure for oxygen. We notice that oxygen is very close to having 8. It's missing 2. And calcium is very close to having 0. Luckily, it's a happy marriage between them. Calcium can give that electron over here and this electron over here. So calcium will donate 2 electrons to oxygen. And oxygen will accept 2 electrons from calcium. Now, looking at one calcium atom, it no longer has any dots around it. We've given them away. You can think of this arrow sign as being equal to. After it's giving up these electrons, it has no more electrons on it. What would its charge be? Plus 2. It's given up 2 negative charges. Oxygen has now gained 2 new electrons, making it now have 8. What would its charge be? Negative 2. Let's look at beryllium and fluorine. Beryllium has how many? 2. And fluorine has 7. So I'm going to draw beryllium. It has 2. Then I'm going to draw fluorine. It has 7. This fluorine is missing 1. It's missing 1 right there. Luckily, this one has 2 spare. So it's going to donate 1 of the electrons and fill up that fluorine. But we have a problem. Beryllium still has an extra dot next to it. Again, they want to either have 8 or none. What are we going to do with this additional dot? Keep your mask on. What'd you say, Michael?
Just get rid of it.
How do we get rid of it? Fluorine already now has 8. I've given it, so it had 7 to begin with. I've given it 1 electron. It now has 8.
Give it to another.
Give it to another fluorine. I'm going to get another fluorine. And this new fluorine is also missing 1. Which is fine because this beryllium can give it that extra 1. So looking at the beryllium atoms, all the beryllium atoms has given up their electrons, so they have no dots next to them. What would its charge be? Plus 2. It's given it up. And looking at the fluorines, each fluorine has gained 1 electron and now has how many dots next to it? 8. And what would their charges be?
Negative 1.
Negative 1. Again, each of them have only gained 1 electron. But how many are there? 2. So we put a 2 down here. And look at this formula. The formula, whenever you take beryllium and add fluorine to it, comes out to be beryllium F2. Because we needed 2 fluorines. So beryllium will donate 1 electron to each fluorine. Each fluorine will accept. We'll put parentheses. Donates 2 in total. 2 electrons in total. Each fluorine will accept 1 electron. So beryllium gets a +2 charge, while each fluorine gets a -1 charge. Seem pretty easy? Alright, let's do number 11. It's probably not going to fit in the box. I mean, you can get it to fit. But I really like to draw it out to illustrate it. So what is the formula for aluminum when mixed with oxygen? What is this formula right here? So aluminum and oxygen. How many valence electrons does aluminum have? And Michael, keep your head up. It has 3. How many does oxygen have? 6. So let's draw aluminum. Aluminum would have 3 dots next to it, while oxygen would have 6. So it just needs 2 more from it. So this 1 dot is going to come over here and fill this hole. This 1 dot can come over here and fill this hole. Now oxygen will have 8 around it, but we have an additional aluminum. So what do we need to do?
Add it to another oxygen.
So we're going to need another oxygen.
But the oxygen ain't gonna be full though.
The oxygen.
So I can come over here and give it 1, and you're right. Oxygen is not full. It needs another electron. So we're going to come over here and get ourselves another aluminum.
Add 1 to it, then add another oxygen.
Now we have 2 left. So we're going to come over here and get ourselves another oxygen. And this oxygen wants 2 electrons, which is fine as this one has 2 to spare. So this equals or goes to, we look at the both elements. How many dots are now around all the aluminum? None. They've given it away. So what would their charges be? +3. And where all the oxygens now have? 8. And their charges would be?
-2.
And how many aluminum do we have?
2.
How many oxygen do we have?
3.
So this makes Al2O3. The aluminums get a +3 charge, while the oxygens get a -2 charge. So whenever I say the word aluminum oxide, it is not ALO. ALO is not aluminum oxide. It is not Al2O. It's not AlO2. It is precisely Al2O3. This is the formula unit for aluminum oxide. It's 2 aluminum atoms for every 3 oxygen. There's an alternative way, but I think graphically makes a lot of sense, so I can visualize this easy. If you were to write down, so we know aluminum has 3 valence electrons, so whenever you lose those 3, it's going to get a +3 charge. Oxygen has 6, and when it gains 2 negative charges, it has -2. This is known as the crisscross method. I'm going to criss the 3 over here, and I'm going to cross the 2 over here, and I get the same result. The issue with learning the crisscross method is, let's look at one of the first examples we did, calcium oxide. This is the correct formula. So if we look at calcium, calcium has 2 valence, so when it loses it, it becomes +2. Michael, keep your eyes open. Stop lifting your head to the side. Straighten up. Oxygen has 6, and when it gains 2, gets a -2 charge. So calcium oxide, doing this crisscross method, the 2 comes over here, and the 2 comes over here. Are these formulas the same? That's because this is divisible by 2, so we divide both the numbers by 2. That's Ca1, O1, and we omit 1s. And then we get the same result. For example, this is technically water, H4O2. But we don't say water is H4O2 because this is not a formula unit. A formula unit is the lowest ratio of these numbers. So 4 to 2, it's actually called empirical unit. We can divide these by 2. H2O1, but we don't say H2O1, we say H2O. We omit 1s and we always reduce down. But you can also do this graphically instead of doing crisscross too, and you get the same result. So, magnesium and fluorine. What's the equation for it? Well, we have magnesium and fluorine. What group number is, or how many valence does magnesium have?
2.
2. And fluorine? So magnesium gets 2 dots. And fluorine will get 7. We know that this is going to come over here and fill that, making it 8. And we need another fluorine atom to take the other electron. So magnesium is going to get a what charge? Positive what?
Positive
2, because it's giving up 2 electrons. The fluorine is going to gain 1 electron because it gets a -1 charge. And there are 2 fluorines. So our equation is MgF2.
-1.
Yeah, -1. Alright, sodium and fluorine. Sodium's what group number? And fluorine? So 1 dot for sodium and 7 dots for fluorine. So there's an empty spot right here that this electron can go. That gives sodium a +1 charge and fluorine a -1 charge. So the formula is NaF. Another way of looking at this is all compounds have no charge. So let's look at aluminum oxide again. This has no charge. We have 2 plus 3 charges, and we have 3 -2 charges. 2 times +3 is +6. And 3 times -2 is -6. What happens when you add +6 and -6 together? You get 0. Because all compounds have no charge, only ions do. And all ions try to come together to make compounds. So sodium, we know, has to have a +1 charge. Fluorine has a -1 charge. And when they come together, they cancel each other out, giving us 0 charge for NaF. Going back, this one here too. This has a +2. That has a -2. When they come together, they cancel each other out, giving us 0 charge. Looking at the previous one, MgF2. Magnesium is a +2 charge, while fluorine is a -1 charge. In order to make these sum together to equal 0, we need 1 magnesium for every 2 fluorine. That's our +2, and 2 times -1 gives us -2, making us have 0 overall. So we have to double the -1 charges to counteract the +2 on the magnesium. So let's look at lithium oxide. Lithium is how many valence?
2. 1.
1. Michael, wake up. Stop drifting off to sleep. Oxygen has how many valence? Oh, draw that too big. Alright, so I can come over here and give that there, but I'm missing one right here. So I need another lithium that will come over here and fill that hole. So I need 2 lithium for every 1 oxygen. Another way of thinking of it is lithium is a +1 charge, while oxygen is a -2. To cancel out this -2 charge, I need 2 lithium atoms. So lithium gives away its electrons, giving a +1 charge, while oxygen, the single oxygen, receives 1, or receives 2, giving it a -2 charge. Let's look at potassium sulfide. Potassium has how many valence, Michael? Keep your eyes open. 1. Sulfur has how many? 6. And come over here and fill that spot. If I need another one, come over here and fill that one. So what's the charge on potassium? +1. What's the charge on sulfur? -2. And there are 2 potassium. So the formula is K2S. And again, on the right is ions, so we put brackets and charges around them for doing Lewis dot. On the left, we used just the normal Lewis dot for atoms. And we usually don't do these dash circles to illustrate the holes. Usually sulfur is just like this, without those invisible circles, but it might help you when drawing these arrows to actually see where the holes are. Alright, last one we'll do on this, magnesium oxide. So how many valence does magnesium have? Oxygen has how many?
6.
What charge will magnesium have?
+2.
+2. And how many will oxygen have? -2. So magnesium has 2 dots.
Which is the charges, whatever it gets added to it.
What now?
So the charges are whatever gets taken away or added to it, like if magnesium gets taken away,
It becomes positive. And if you're adding 2 negative charges, it goes to negative.
that works.
And so the formula is MgO. Make sense?
You finish this up?
I'll do just one more. Just show you the answer. So aluminum has 3. Chlorine has 7. So that means that aluminum can only give 1 electron to each chlorine. So we need 3 of them. So the formula would be AlCl3. There are 3 chlorine for every 1 aluminum. So, looking at these group 1A has 1 valence electron. And what charge will they have whenever they become an ion? +1. Yes. Group 2A has how many valence? And what is their all charges? They get +2 ions. Group 3A has how many valence? And what charges do they get? +3. Group 4A has how many valence? What charges do they get? +4 or -4. They're right in the middle. They can either gain 4 electrons and become -4, or they can lose 4 electrons and become +4. 5A has how many valence? 5. What charge do all of them get?
-6.
-5.
-3.
-3. They need 3 electrons to get to 8. Again, the test is it closer to 0 or is it closer to 8? If it's right here at 4, you can either add 4 electrons and get to 8, or you can lose 4 electrons to get to 0. So we can add 3 electrons with 3 negative charges, which makes it -3. 6A has 6 valence electrons, and what would their charges be? -2. Oxygen is -2. 7A has 7 valence electrons. What would their charge be? -1. 8A has how many valence? And what would their charge be? 0. They're already at 8. They don't want any additional electrons. Oh yes, but we won't learn them. For example, if you want, out of curiosity, lead. What charges does lead get whenever it becomes an ion? Actually, let's see if I can find it. I got a list of common exceptions. So what would lead be, do you think? What charge do you think when it becomes an ion? So +4 is one of them. And +2. 10 is the same way. Antimony can either get +3 or +5. Again, these are exceptions. If we look at them, all the halogen group 7 gets a -1 charge. All the group 6A or 16 get -2 until you get to these heavier elements. These get -3 until you get to these heavier elements, the metals. You'll notice that the zigzag line separates the metals versus non-metals, and technically there's metalloids in here. Carbon and silicon usually don't form ions. Boron neither, but we don't really have to look at this. And then when you get to transition metals, it's very weird. But we come over here, +1, +2, +3. That's a transition metal. But you don't need to learn any of these exceptions. In the other chemistry class, we learn why these heavier elements tend to be more positive. So why do you think they have positive charges down here instead of the negative ones like the rest of them? What does it mean to have a positive charge? You don't know it. You've donated or given away your electrons. And why are electrons around atoms in the first place? You have a positive nucleus that the negative electron is attracted to. Now, what would happen if you have a really big atom where the electron is very far away? You really can't hold on to the electrons as easy. Hence, once you get to these very heavy elements, they tend to be able to more easily give up their electrons, as there's only a ever so weak force holding them together. But in this class, we won't worry about the exceptions. We're just going to look at the group A elements and work with that. But I would like to do just one of them. One transition metal. Iron. So iron can either be 3 plus or 2 plus. So whenever we have a chlorine ion, so an ion of chlorine, it's Cl negative, or Cl negative 1. What is the name of this? His name is chloride. The "ide" tells us it's an ion. So when you do sodium chloride, I'm saying I have a sodium with a negative chlorine atom attached to it. We don't have special names, so this is the anion, the negative ion, and this is the cation, the positive ion. We don't do anything special with cation names, so it stays as sodium. So a sodium ion is still called sodium. It would just be called a sodium ion. But a chlorine ion is called chloride. The exception would be if they have multiple ones, we have to distinguish these two. This is called iron 3. And we use Roman numerals. And this is called iron 2. So, here's the question for you guys. What would iron 3 and oxygen make? So, oxygen is negative 2.
You make rust.
It would make rust. What would the formula be?
F2O2.
Fe2, you forgot the E, O3. This is called rust. Now, what would happen if we instead used Fe2 plus and O2? O negative 2. So FeO. These two charges cancel each other out. So what is this? Is it this iron oxide too? Are these both iron oxide? Is this rust too? This is not rust. If you say iron oxide, you are very ambiguous on what chemical you're talking about. Meaning you're uncertain. The technical name for rust is iron 3 oxide is rust. This is actually a pigment used in tattoo. Michael, wake up. John, head off the desk.
So, it's iron in tattoos.
Iron 2 oxide is. It's a pigment. Which is very different from iron 3 oxide. Like, these are two completely different chemicals. Just like H2O is what? Water. And H2O2 is what?
Also, what?
Hydrogen peroxide.
That's true.
How many elements you have matters.
No.
Don't have a video showing all my efforts.
I think there's a piece of it. So, what you do is notice
All right. How do we see if so all of this that we've been doing only works for ionic bonding.
So are we gonna be doing anything from this? Like this?
Yes, this is basically the test.
Can I go right on?
Mhm.
The exception that we're only gonna have on like Fe and O.
I'll tell you what the charge is on Fe. Oxygen you should be able to figure out. These exceptions, I will specifically tell you what it is. For my real chemistry class, I ask them what happens when you make iron with oxygen. And they have to be able to tell me, well, you get two things. You can either get iron 2 plus or iron 3 plus. They have to know what all these exceptions are. You guys don't, I'll tell you what they are. But all of this only works for ionic bonding. Let's look at iron. Iron 3 oxide. Is this an ionic chemical? How do you know? So, the number you need to look for is 1.7. What is iron's En value? So iron is right here at 1.8. So it has an En value of 1.8. What is oxygen? 3.5. So what is the difference in En values? So 3.5 minus 1.8. 1.7. So this answers your question. We do call this ionic. Just barely though. This is almost not ionic. Again, it's a gray fuzzy line at 1.7. What about water? What is the En difference for water? So oxygen is 3.5. 2.1 for hydrogen, so 1.4. Not ionic. What would the En difference for hydrogen peroxide be? What do you mean don't know? It's the exact same. We only have hydrogen and oxygen.
So those two.
The subscripts do not matter. Subscripts play no role on checking whether or not it's ionic or not. So H2O versus HO2. So let me ask you this. What about iron 2 oxide? Is it ionic? What's its difference in En? Well, there's only iron oxygen, so you should know it's equal to 1.7. I didn't change anything. These subscripts do not matter. Only what elements you have. So it would still be ionic. Barely, at least. Let's do this one. C12 H22 O11. What's the name of this chemical?
Acid. Carbon water.
It's known as table sugar. What's the other name for it? It's the chemical name? Sucrose. So this one's weird. We actually now to compare all three of them. So when checking, we're checking to see if there's any ionic bonds. So we're going to choose two elements. Let's look at carbon bonded with a hydrogen. Does this form an ionic bond? Carbon is 2.5. Hydrogen is 2.1. So that's a difference of 0.4. So that is not an ionic bond between the carbons and hydrogens. What about the carbons and oxygens? Carbon is 2.5, oxygen is 3.5. That's an En difference of 1. What about carbon and oxygen? Well, that's 2 point. Carbon,
Oxygen.
hydrogen, and oxygen. Well, that's the water example we did over here. 1.4. So, no matter how many combinations of what this is, there's no ionic bonds anywhere in it. Every possible combination of one atom bonding to another, they're all not ionic. The reason why we ignore subscripts is, again, we're testing in between the bonds. So we're looking at asking, is this bond right here ionic? And the answer is no. And by symmetry, this bond would not be either.